part, I'm starting at the other end, the extreme. So I'm in a material science department. Generally, we care more about solid things than liquid things. So I approach the viscoelasticity more from the solids end. But there will certainly be some connections with the sort of things that Ralph Colby talked about as well. So like the last time, there will be some introductory stuff, basic viscoelasticity things, and then some examples of there's a correspondence principle. Every field has their correspondence principle, but in this field, what I mean by it is if you know the elastic solution to a problem, and it's the same loading, but it's an oscillatory loading, then you just replace the modulus with this complex modulus. So we'll talk about that a little bit. So this is what you always start with. So when I give my lecture on viscoelasticity, I have the silly putty, which I didn't bring with me. But you bounce it on the table and it does this. I thought that this was just a relatively archaic kind of illustration, but it turns out that someone is actually doing this kind of here. I'm not sure where you are, but basically doing this with very soft gels. It's a pretty interesting experiment, at least the elastic part. But with a truly viscoelastic material, or at least a version of viscoelastic materials, if I let the thing sit on the table, it just flows. So short times, it's a solid, kind of long time, it's a liquid. So that's what we mean. And slightly more technical, if I have a strain, kind of time-dependent strain that I put on something, if it's a solid, the stress just tracks with the strain. There's a proportionality there. If it's a liquid, the stress is proportional to the rate of strain, so the slope of this thing. So I'm going to have zero stress on either side and some constant stress here where the slope is constant. And if it's viscoelastic, the entire time history matters. So it's complicated. We have to do some sort of integral. But it turns out it's not that complicated. We can do this relatively straightforwardly. So there are two ways to do this. So I think the most intuitive experiment, and you've heard about this already, is a stress relaxation experiment where at some time zero I just put an instantaneous strain on. And that's kind of your first clue that this maybe is not the way we always do these things experimentally, because nothing is ever instantaneous in an experiment. But it's a bit of a thought experiment. You do that straight away, and you just look at the stress over time, divide that by whatever your constant strain is, and that now gives you a time-dependent modulus. So a more common way to do this is in oscillatory mode. And in these experiments, it's almost always going to be shear. So I'll use G as the relevant modulus. So I just apply an oscillatory strain and look at the stress, which is also, if it's linearly viscoelastic, so the stress is at least proportional to the magnitude of the strain. Then I'm going to have a sinusoid in, a sinusoid back out, and there's going to be a complex modulus. And the magnitude of this thing is just going to be the magnitude of the stress over the magnitude of the strain, but there's going to be some phase lag between stress and strain as well. So there are these two ways of looking at it. And probably the most formal thing I'm going to do, which I don't think has occurred yet, is actually how you make the connection between these two things kind of mathematically. But first, a couple examples. These are just kind of single exponential relaxations, which we never really have. So this is an exponential relaxation illustrating kind of a relaxation maybe from a glassy modulus to something much softer. So the time dependence would like this if it's just a single exponential. So like this one here, which again, it's never really what you have. But I put this up here to show that the relaxation times typically have some connection with what's really going on physically in the material. So this would be sort of a relaxation from a glass. If it's a high molecular weight polymer, they're entanglements. So there's a longer time it takes actually for these entanglements to relax. And if I cross-link the thing, so instead of just having a physical uncrossability constraint here between these long molecules, I actually have a chemical cross-link that can't relax, and this just goes all the way out to infinity. And down at the bottom, these are the ways people look at these things. So there are cases which are pretty nearly single exponential in their decay, but not that many of them, at least in the solid things I'm more interested in. But if you take enough of these single exponentials and add them up, you can fit anything. And often these relaxation times correspond to specific processes. So this is why a proper rheologist generally kind of likes this the best. But sometimes there are kind of empirical fits that just work, or there might be just regions where you actually have different behaviors. So a power law kind of behavior is one. So we saw this example early on, a polymer that you kind of cross-link, and right at its gel point, it basically has a power law response, which is equivalent to saying there's some very large distribution of relaxation times that you have. And the glassy time, you can actually do both an exponential relaxation and an exponent. So that's the S stretched exponential or KWW form. My experience, rheologists get a little bit grumpy when you kind of do things like this. They like the single exponentials. So even Ralph Colby had to apologize when he basically was using kind of that form. But it's still a useful way of sometimes representing your data if you just want, again, the curve to go through the data, but sometimes that's what you need. So that's what the relaxation modulus is. Yep.
Is that the relaxation of just the elastic modulus, or is like the viscosity also the...
Well, it's got units of an elastic modulus, so units of a stress, but it's time dependent. So these things are just different fitting functions to express the time dependence. So it's no longer a constant anymore. It's a function, right? So these pictures are all just representations of some time dependent function.
But it's just for the elastic modulus. It can be also for the viscous modulus.
Viscosity, elasticity, it's all in here, right? So I do the same thing for a liquid. So at this point, it says nothing about whether it's behaving more solid-like or liquid-like or what. Yeah. And so, yep. So change the time, you say, or?
Is there a physical reason why it shouldn't be an increasing function with respect to time?
Yeah, I mean, so the question is, can the modulus increase with time? I don't know what it's unphysical, right? It has to decrease. You're violating some kind of physical law. Probably Michael would be able to tell us what, but it has to decrease with time. And there's when we start talking about frequency-dependent modulus, the magnitude of that has to increase with frequency for similar reasons. So it's got to relax. It can't go up. Yeah, you would basically be creating energy, I think, if you increased with time. This is kind of Boltzmann's superposition principle. So I mentioned that for a viscoelastic material, say I meant to actually have a horizontal line here. So suppose I have this kind of strain history. So I put a step strain there at that time, leave it constant for a while, another step strain here, another step strain there. And at this time here, I look at what's actually happened. And Boltzmann's superposition is pretty simple. All it means is that I look and just add up independently the effects of all these strains. So S is a time variable. So I start here. This first one has had this time S1, that much time to relax. So it starts here, relax to here. Then I bump down here. That one has had, so now there's a negative kind of component to the stress that I'm putting in. That's had S2 to relax. And then another one here, S3. So I just sum kind of all these components up, and they all have their relaxation time. So the amount of stress that's left is just G of S, basically. So I multiply by kind of the strain that I kind of put in at any given time. So that's the strain, and this is how much is left after a given time. And if I want to do this in the continuous limit, I just kind of integrate kind of all these effects. So I start here in my current time that I'm interested in, and I basically integrate backward in history. So that's what is going on here. So S is a variable, how long ago this was. T is my current time that I care about. And the integration here is over the strain rate because I need to multiply the strain rate by some time increment to basically get what my individual contribution is. So this is just the fundamental equation that allows you to, for a linearly viscoelastic material, which means since stress is proportional to strain, it doesn't matter when it occurred. Basically, I can just do this integral and kind of figure out what's going on. Steady shear, what that means is I do this, but now a case where my strain rate is constant. So everything just kind of falls out, and the viscosity now, which is just the stress over the rate of strain, is just the integral of this relaxation modulus. So the dimensions work out, right? This is Pascal integrated over time. So this is Pascal seconds. So there's a 0 here because that means that viscosity is generally strain rate dependent. We kind of know that. And this assumes that we're not going to build up so much stress that we get into a nonlinear regime. So the 0 here just means it's a limit of this thing basically going to a 0 strain rate. So eventually, if it's liquid-like at all, you're going to reach some sort of limit. So that is kind of how to use it in steady shear. Oscillatory shear, it's the same thing. So you don't have to kind of follow all the details of this, but it just kind of works out to be a sine or cosine transform. So this is what we do in oscillatory shear. And so I put in a sinusoid with some magnitude and some angular frequency. So gamma dot that I'm going to use in my Boltzmann superposition equation is just the derivative of that. So the frequency kind of comes out. This turns into a cosine, or we can kind of write it this way, which is a bit more convenient. So you see pi over 2 or 90-degree phase shift between stress and strain. Between strain and strain rate. And then we kind of, this is our equation for Boltzmann superposition. And I go through and kind of do that and see what you end up with. And you have this part here. So this is the equation for the stress. You have this part, which goes like sine omega t. So that's basically a part of the response which is in phase with my strain to begin with. And I have this part over here, which goes like cosine omega t. So that's the part which is going to be in phase with the strain rate. So the first part we just call the storage modulus G prime. This other part we call G double prime. So and there are a few ways to kind of use those. So here's just illustrates what's going on. So if you have a liquid, you have a phase angle of 90. So the stress and strain are going to be 9 degrees out of phase with one another. Viscoelastic material. So this, we'll see an example of this, but if you have a material which is sort of in the lingo of previous lectures, if all your Rouse modes are active and you're basically in between kind of the rubbery regime and the glassy regime, you're going to have something closer to 45 degrees for a phase angle. And there are different ways to do this. So my preference, and what I'm going to do mostly, and this isn't the way that the rheology community always does this, but I think it makes things a little bit simpler, and the math gets a little simpler for other things I'm going to do. So you can either think of this as a complex modulus, so the star just means it's a complex number. So I can view that as something that has a magnitude and a phase, or a real and imaginary component, and this is how they're connected with each other. So the magnitude, again, it's just the stress amplitude divided by the strain amplitude, and the phase, you kind of see what that means over here. And you can use those things together then to get G prime and G double prime. You've seen this, I know at least in the lecture that I heard from Ralph, and I think others as well, kind of time temperature shifting. And he mentioned, I think this is the rule of thumb, if a frequency is, Well, if it gets much bigger than something like 100, this is angular frequency, then it must be time temperature shifting, which is actually work, because this is sort of a traditional rheometric range, I guess. So you can go lower, but so this is just an amorphous polymer. So that glass transition, the details really don't matter here too much. I'm more interested in kind of how you actually get this. So this is kind of increasing temperature. And you know, one nice thing about just kind of looking at the magnitude of this is that the magnitude always has to basically decrease with temperature and basically increase with frequency, just like I'm showing here. So this is what you actually measure. And you shift these things along this axis. So the assumption with sort of time temperature superposition, which is what's going on here, is that you have a distribution of relaxation times, maybe not one exponential, but some broad distribution of them. You assume that all of the relaxation times get multiplied by the same amount when you change the temperature. So basically the shape of your relaxation time distribution isn't changing. And you just empirically do this sort of by hand somehow, or usually the rheometer kind of spits it out at you. But this curve gets shifted over the left, that one gets shifted over the right to overlap with this red one. And those shift factors are dependent on the temperature that you use. So that's the raw data. And this is what the shifted data actually look like. So in a case like this, it works beautifully. This is about, it's as simple as it gets. And someone was commenting, I think before, why is your data so smooth? And it's kind of a truism that if you really want good looking data, you do the right rheology experiment, and it's really kind of very clean data that you actually get out from it. So the only question here then, what finishes the story is, well, what shift factors do I actually use to actually do this? And those shift factors, again, give me the temperature dependence of the relaxation time. And this is what they look like in this example. So these are all the temperatures that I actually use. And then there are a couple different forms of this. Yep. Excuse me? Yeah, I'll get to that a little bit. So this is, let me work through this, and I think in the process I'll answer that question, basically. The answer is that you can go to around TG. Here, I'm still about 25 degrees kind of above TG, so it just kind of depends how much patience you have to actually do the experiment. But these shift factors kind of obey equations like this. There are two mathematically equivalent functions that are used. This one's called the Vogel-Fulcher-Taman equation. There's another one called WLF, Williams-Landau-Ferry equation. So WLF, VFT, they're the same thing. I like this one better because I look at that equation, I understand what it looks like a bit more than the other one. So it's just the log of the shift factor. That's a log scale there. And it looks like basically an Arrhenius behavior, but our effective zero in temperature is shifted from 0 Kelvin to this thing here, T infinity. And there's a bunch of theories, approximate models, I guess pictures of what this might actually correspond to. The important thing to keep in mind, though, it's always determined by fits that are well above this T infinity. So it's easy to ascribe kind of more to that physically than it really deserves to get. And so we're always kind of fitting kind of forms like this. And it turns out that this number, 1500 Kelvin, is the unit it has, is fairly universal. It's almost always between 1 and 2000 for kind of standard polymers. And this T infinity is usually, rule of thumb, about 50 Kelvin kind of below the glass transition temperature. So you're extracting, and that determines the curvature where this would extrapolate up to infinity. So you're determining this by basically fits well above T infinity. But this is kind of how we think about this, and you've seen a lot of shifted data already, so I at least wanted to give kind of one example. And it's going to be important in our experiments because we're going to be working at very, very high frequency. So to make the comparison back to low frequency data, we need to understand how to deal with the shifting. This I actually found from the literature. It's tough to find kind of nice literature data that you can kind of plot yourself. But this kind of 20-year-old paper down here at the bottom, they actually, for an epoxy material, give basically it was a 20-element fit, so 20 different exponentials. You just add up and you can plot it however you want. So this, in that case, is what this modulus looks like. Not exactly sure what the reference temperature, that's where the shift factor is equal to 1, is for this. But this is kind of what you expect for a relatively highly cross-linked network. So this is either high temperature or low frequency. And the glassy modulus here, excuse me, you get up close to 10 to the 9. So that's what the modulus looks like. What you expect, I actually haven't looked at this thing real closely, but you expect a slope here of about a half. And so here it looks fairly straight line on this log-log plot. So this looks like a power law behavior. And if you have a power law behavior with a slope of a half, you'd expect your phase angle to be 45 degrees, which is also what you get. So the important thing is that there's a connection between how fast this is changing in frequency or temperature and what your phase angle actually is. So in the elastic limits on either side, those things are flat, low phase angle. We have a high change here, you have a higher phase angle. So that's how I'm doing for time here. Okay. So that's the just kind of the basics of viscoelasticity. Again, I think fairly consistent with some things you've already had. Let's look at a real problem now. And this is the correspondence principle. This is the example I'll show. And this is going to make the connection to how we're actually going to measure kind of viscoelasticity in some of our materials. So this is a torsional resonator. So this is a spring, and the spring is just a polymer fiber. It's got these dimensions and a typical glassy polymer modulus around a gigapascal. So there's a torsional stiffness. We can kind of look that up somewhere. It depends on the shear modulus of the fiber. So a twisting like that is a pure shear kind of deformation. That's the only modulus that shows up. And the angular frequency, so if I twist this a little bit and just let it go, this is the angular frequency that I would expect to get. So the moment of inertia of that mass at the bottom, we can also look up. Put all the numbers, and I get basically 2.6 inverse seconds for the angular frequency. So it's a, about half a hertz or something like that. The period of the oscillation is maybe 2 seconds. So what the correspondence principle is that, okay, now it's viscoelastic, and it's not very viscoelastic because G prime here is 10 to the 9 still, but now I'm going to make a non-zero G double prime. So this is the part that gives us the elastic character. So the tangent to the phase angle here is 0.01. So that's a bit, it's like a half a degree phase angle, which is pretty typical of what you get for a real glassy polymer, reasonably far below the glass transition. So I do the same thing, except now instead of G, I've got a complex number. So that means K, I use the same equation, that's also going to be complex. And omega is also going to be complex. So I just put in all the numbers, keep all the complex stuff there. And what I end up with is an angular frequency, which has a real part and an imaginary part. For these numbers, the real part is more or less unchanged. But the imaginary part here is 1.3 times 10 to the minus 2. So it's quite a bit smaller than this because the viscoelasticity is relatively small. Yes? Well, I just, up here, so where'd this come from? I just made up numbers for kind of my example here. So this is, it's an example of a sort of a solved problem, which gives me an oscillatory motion, basically an oscillatory stress. And I want to see. Yeah, that's right. Yep. The math is exactly the same. I just put a complex number in. I get a complex number out from omega. All the other math is exactly the same.
You could get it from the plot, on the previous plot was just factor of family glassy regime. You show the glassy regime, right?
What's that?
Yeah, here. If you get your parameters of time from this plot, then you could just read it all.
Yeah, so what I did is, I said kind of way up here. This part. Yeah, yeah. So I'm using basically, I'm using a point up here, and sort of to convert this to G prime and G double prime, but a kind of phase angle down here. And it turns out the phase angle isn't really very accurate. A more accurate way to measure is to actually do this and see what you get. What's that?
You're taking a oscillatory frequency.
Yeah, that's right. Yeah. Yeah. So, yeah, that's right. I have to make sure I'm using the value of G that corresponds to this frequency, right? Yeah. So this is what you end up with. So what the dissipation does, this makes sense, is that it's not a perpetual motion machine. The oscillation dies down. And here, the only reason it's dying down is because the small amount of viscoelasticity, the energy loss kind of in the material. So a non-zero phase angle gives me this. And this is an important number for kind of a resonator, which is this thing Q. It's the quality factor. Basically, it's kind of when the amplitude of the resonance goes down by a square root of 1 over E. So if you count how many things I have here, I get 16 of them before I get to that point. So 16 is the quality factor of this resonator, which is not a very good resonator. So if you think about a tuning fork or a bell or something like that, where you kind of hear a sound at a few thousand hertz, and you hear it ringtone kind of last for a few seconds maybe. So that's going to be a quality factor in the thousands. So this is a pretty crummy one, but it's about as good as you can do with a glassy polymer system because the phase angle is pretty low. Okay. Yep. So what the experiment would be? Yeah, so what I'll do is I would take this, kind of hang it from the thing, twist it a little bit to start it going, and just let it go. And it kind of goes back and forth, and I measure the period of the oscillation. So theta is just the rotation angle of this whole thing. No, it's just in air. The only dissipation is the dissipation in this fiber. But that's enough, even for it's a 0.6 degree phase angle to really kill the oscillation relatively quickly. Yeah. And I'm going to talk a lot about resonators later, so it's this connection between dissipation and how well the thing oscillates that I wanted to keep.
Viscoelasticity is fundamentally the harmonic motion?
Yeah, that's right. If you have viscoelasticity, it's going to damp any resonance that's somehow coupled with it. Yeah. And I'll come up with kind of other examples of that. I like this one because it's easy to visualize, I think, what's going on. May not have done a good job, but I'm pulling this and kind of twisting it and look at that thing over time. Okay. Now, here's a 2-minute aside that has nothing to do with what I'm talking about, but it might be useful. This is my opinion, which you're free to disagree with. But what I have found is that we teach all our students MATLAB. We got the license for MATLAB at Northwestern. They get pretty good at it, actually, pretty quickly. But then they graduate, and either they or their company does not pay for MATLAB, or they use an illegal copy, and one or the other. So all my stuff in my group was all MATLAB, and I came in one day and a postdoc had rewritten everything in Python. I said, well, that's pretty cool. And then I eventually have come to this conclusion. So what I do in my stuff is actually include examples of Python code. And in my lecture, I've included a bunch here. And you can also do, if you're listening to I'll use Herbert Hoy as an example because I know he's very good at math and he shows a lot of it. But I look at the math and I don't always see what that means. How does that derivation go? I write it down on paper and pages, and then I realize I messed something up back there and it's all wrong. So the symbolic Python version is actually pretty good. And that I can see what it actually looks like, and it just kind of follows through, and the syntax isn't so bad. I've included kind of what the code is for kind of this stuff, because sometimes you just want to see examples, because I think one of the things that limits people's ability to get up to speed with Python is because you want to know examples how to do stuff. So that's an aside. So if you like MATLAB better than Python, you can talk to me later. Okay, so this gets now closer to the other half, I guess, or so of my presentation and what I really want to talk about. So sound waves is another example of periodic oscillation, where presumably, if I look at a sound wave velocity, I'm measuring the dynamic property of the medium the wave is propagating through. So this is just an illustration of a longitudinal pressure wave. I have linked illustrations here that are animated, but I'm not going to try to work this on a computer that's not my own. I'll mess things up. But it's a pretty small perturbation on the local pressure. And this is sort of accurate, all right? So atmospheric pressure is 100,000 Pascal. So what they're showing here at this location, well, it's 101,307 Pascal. Here in the low pressure regime, 101,306 Pascal. So it's a small kind of perturbation kind of on kind of density of air. And sound velocity is a mechanical property. So it's just given by the square root of a longitudinal elastic modulus divided by the density. And it's easy to calculate kind of what that should be. So I want to talk just a couple slides about kind of different kind of modes of deformation, because this is a strange mode of deformation and kind of what sound is actually doing. This is what we're used to thinking about, shear, and that's what I am actually going to talk about. So in shear, it's the nice thing about a simple shear like this is that I'm changing the shape of something, but I'm not changing the volume of something. So we've seen kind of stress tensors that actually look like this, and the shear modulus G is kind of the relevant one for looking at that. I would say that the complementary modulus, the most obvious one, you have an isotropic material, you have two independent moduli. I would always choose shear modulus and bulk modulus K here, describe these. So this is hydrostatic compression, it's the opposite. Right, the volume is changing, but the shape is not changing. And kind of this is the definition of this, and the stress tensor for just hydrostatic compression kind of looks like that, or tension. Now, sound wave is longitudinal compression. So it's basically constrained, so we're pressurizing in this direction. It's a plane wave traveling along here, so that the volume doesn't, it doesn't change the other direction. So basically it's changing the shape and the volume. So it makes sense that it's going to be the relevant modulus here. So kind of just the linear kind of strain divided by the kind of stress in that same direction is going to involve some combination of the bulk modulus and the shear modulus, and this is what it is for this particular case. So for a gas or a liquid, this is zero, really. So you're really measuring kind of just the bulk compressibility of air. Turns out it's the isothermal compressibility, but that's a bit of a detail. So there's these different things that we have to actually worry about. So, and again, I'm going to be interested in kind of sound wave propagation. So air or water, if I look at the modulus here, shear modulus, I'm not going to get any shear waves, but any solid, so jello, kind of soft gel, kind of typically 10 to the 4, a rigid plastic polymer, kind of 10 to the 9, steel, getting close to 10 to the 11. We have these sort of modulus. But if it's a longitudinal wave, basically that goes in air, because there's a bulk modulus for these other things. So these are just kind of representative values. And if you forget all the, I have 2 independent modulus, kind of which ones I choose, you can get all the other ones from that. So if you want something as a function of bulk modulus and shear modulus, well, that's Young's modulus. Let's see, that's Poisson's ratio. This is actually the longitudinal modulus, so I'm talking about. I'm not going to worry about that other one. So it's easy to kind of find these things. So that's a bit of an aside. What we're going to be looking at is shear wave propagation kind of in a solid material. Okay, so this is what the rest of the talk is really going to be about. So how do we get these shear waves? How do we actually cite them? So this is a picture of the common name for this is quartz crystal microbalance. A lot of you may have heard this as a very sensitive way of measuring kind of mass in materials. So this is single crystal piezoelectric quartz. It's a pretty thin disk. It's about 2.5 centimeters in this dimension and 1/3 of a millimeter, 330 microns in this dimension. You can get different sizes, but this is a standard one. So each disk costs about $25 or $30, probably more now. And it's piezoelectric, so if you have an electric field that you put on that, this is cut so an electric field across it in this direction gives you a shear in this direction. So if the, and it's actually a pretty small displacement unless you're at resonance. So there's a resonance condition, which is just given by if the time for a shear wave given by kind of square root of the modulus over the density of the quartz. If I excite a shear wave by translating this top part, that translates down here, bounces off the bottom surface, comes back. And if that corresponds to 1 period of the oscillation, then I have a fundamental resonance of the crystal. And that resonance is very, very sensitive to kind of very small perturbations, kind of how I touch things on the top. I'll show you kind of the master equation for all this in a little bit. So if I have a film up here, or some material that's in contact with that, I'm oscillating it now, so it's resonant. And there's only kind of one resonant frequency. Actually, it turns out I need multiple harmonics. So for this geometry and mechanical properties of quartz, the first harmonic is at 5 megahertz. We typically measure 3rd and 5th harmonic. So because of this geometry, you have antinodes. So basically, the top and bottom surface are moving. You get a resonance when the thickness is half of the wavelength, and 3/2 the wavelength, and 5/2 the wavelength. So that's where you get different kind of resonance where you can actually measure things. And I'll show you how you do this. Just a couple thing about the technique itself. So this is the range of thicknesses that we typically have. Film thickness matters, film quality matters, and it's only measured as fixed frequency. So those are big limitations, but there's still some interesting things that can be done. So it's very much a special topics thing, but it's an example of kind of using linear viscoelasticity. What's that? Well, it's going this way. So basically, the displacement is just kind of parallel to the film that's on top of it. Are we displacing using physical? So you mean, why do you get shear in the first place? Yeah, that's just the piezoelectric properties of the quartz. It depends how you cut it, but quartz is non-centrosymmetric. So that means if you put an electric field in one direction, you're going to develop strains. And if you cut it in the right direction, if I put an electric field through this way, it actually moves this way. And it's very little motion perpendicular. It's all just doing this. So it's just the magic of the quartz itself that this produces a shear displacement. And it's very small. So typically it's maybe angstrom level displacement. So it's a very much a low strain measurement. So what we're doing, one way of thinking about it is this now is going to propagate a sound wave into this material. That sound wave comes up here, bounces back, and I'm going to get a response which depends both on the thickness and on the viscoelastic properties of this material. So that's how it is going to work. So it's most commonly used as a mass sensor, so Microbalance. And this is there's literally thousands of papers kind of written about this topic. The reason I mentioned kind of what the quality factor is, 16 is a pretty crummy oscillator. This has a quality factor of about 100,000. Quartz itself has very little viscoelasticity, it's a very good kind of very stable resonance, and you'll see what it looks like in the frequency domain a little bit. So here, this thing is kind of moving back and forth like this, and if I put a small mass on there, there's going to be some inertia kind of with this mass, and even if there's no viscoelasticity at all, that's going to change the resonant frequency. And there's, for very thin layers that are pretty stiff, there's a famous equation called the Sowerby equation, which relates a change in the resonant frequency basically to the mass here. So rho is density, d is the thickness. So the product of those two things is just the mass per unit area. So this is how it's typically used. There are a couple ways of doing this. There's the instrument, there's a group in Sweden. So some of you have probably heard about a QSense kind of instrument, which is a time domain instrument, which means it's like those pictures that I was showing before where they actually measure kind of the resonance, the electrical signal you actually get back out. And there's some decay time that they actually measure. So they get the resonant frequency and the decay time. If you do it in a frequency domain, so this, I'm showing it 0 here, but that's really the resonant frequency. So this would be, for example, 15 megahertz. And you measure two things. One is kind of, so this is the conductance. So you do a network, you hook up a network analyzer on this thing, and you just measure the ratio between the currents and the voltage. So you get again, an in-phase and out-of-phase component. The conductance is the in-phase component. That's got a maximum where the thing is at resonance. And this is just because when the crystal is mechanically soft, it's also electrically soft. So it basically conducts very specifically at that frequency. If I put something on it, a small mass or a little bit, the shift goes down to lower the frequency goes down, and also broadens a little bit. And this gamma, it's the half width of half max of this thing, is directly related to the quality factor. So it's inverse to the quality factor of the resonator. What you can do, so we have a complex quantity, which is going to be G star, which ultimately is going to follow all the way through a whole bunch of math to a complex measurable, which is going to be F star here. And that the real part of a complex resonant frequency is just that, and the imaginary part is gamma. So those are both measurable, and we can get these at different resonant frequencies. So I didn't expect this, but Dietel Johansson is basically the hero of this field. He's represented at this conference. There's a student of his around here somewhere. I'm not sure where you are. But one thing that he talks about in here, there's a lot of math in here. No one understands the physics of this better than he does. But this is kind of the magic equation that actually kind of makes things work. And this is a really accurate approximation. So this resonant frequency shift, this complex resonant frequency we can measure, it has a bunch of known quantities here. So F1, that's the fundamental resonant frequency, 5 megahertz. This is the acoustic impedance of quartz. And this is the load impedance of what we're measuring. So the surface of the quartz crystal, the gold electrode surface, is going back and forth like this. And there's a load impedance that feels, basically, with just the ratio of the shear stress to shear velocity kind of at that kind of surface. So I measure this, I use this equation, I get this. And then there are lots of kind of models about what this would be. If I have a thick film of a material, so I put it in water, the load impedance is just this. So I'm measuring kind of the complex shear modulus of water, for example. And you can actually do this, get pretty accurate viscosity measurements at these high frequencies by doing this. Yeah.
How do you deal with Wellington depth in the material? Because like such high frequency, you need to like have very few thickness for the material to be affected by the mechanical shear.
Yeah, so I didn't get all that. You're asking about the thickness? Or so needing to measure it, or?
No, because I mean the sample needs to be need to see all the shear. So if it's too thick and at such high frequency, I don't really think that you can like sample everything. So how do you deal with that?
Yeah, I don't know if I'm catching the question right. Let me continue with what I have, and yeah, let's follow up kind of later on. Yep.
I just want to know what is so special about the quartz crystal rheometer? I mean, why are we talking about this?
I'll give you some examples of what we've done with it. So far, yeah, a lot of people ask that question. Well, so what? Yeah, that's right.
Viscosity at the metaphor frequency.
What's that?
This is the viscosity at the metaphor.
Yeah, that's right. Let me actually answer that question first. So actually, I'm going to do the examples of what we actually do with it and not worry about this. But there's something to say. Here's the point of this slide. There's a mathematical theory kind of behind all this. Okay, so I need to say something about actually how the information is obtained. So this isn't so bad. This is basically all the math that there is. You can solve all these things. So in the end, what you're doing is basically solving 3 equations and 3 unknowns to get the information that I'll show you. So, and what I want to do is kind of show some examples of kind of why we're doing this. And I agree that this is actually very detailed relative to other things you're actually seeing. It's very much a kind of a niche technique. But there is a point in data analysis which this is a good example for. So bear with me for kind of one more slide. So what we do is we measure 3 different things, and we get 3 different properties back out. Basically, the mass per area, we always get that. That's what we're used to. And basically, the magnitude and phase of the frequency at where we're actually resonating. This is a little complicated. You don't want to do this, and this happens, and we see lots of examples of this, and a lot of controversies in science really have to do with this sort of thing. I said the math isn't so bad, but you look at those equations, it's you don't visualize exactly what's going on. A simple model fit by itself is not good enough. The question is, well, the data that I measure, what range of properties are consistent with these measured things? And you more or less have to take my word for it that we've been very careful about all this, but I'll show you some of the examples. Okay, so why do we care? What's the ability to do this? So paint is a pretty important thing, right? And curing of paint matters. This is kind of the first example that we actually did with this quantitatively. So this, a lot of the context here is in the art conservation community. So this is an alkyd paint that some 20th century artists have used, but also if you get your floor painted with something, there's a good chance that it's an alkyd kind of coating like this. It's basically an oil-based kind of side chain, cross-linking it through these double bonds. And it's a polyester backbone that looks like this. So we'd like some data on how this stuff actually cures. But it cures by contact with the environment. So this only cures when it's able to oxidize. So if I do traditional rheometry, I have 2 surfaces like this, and I do this, I'm done. I can't say anything, right? Because the oxygen can't get in to cure. So what you want is a surface-loaded rheometer. So I'm only kind of loading at one side. And basically all the examples of this take advantage of the fact that I'm just, it's a rheometric measurement, but I'm only supporting the thing on one side. And it's also helpful that it's thin, because this cures into a glassy film. These are going to be about 5 microns thick. And paint films have if it's a 200 micron paint film, early stage, it's going to have a a skin layer on top, which gets rigid, and that kind of does everything. We get around those effects here, because basically the entire sample is the skin layer. So this is kind of what you kind of end up with. So this is kind of one of the 4 examples that I'm actually going to show for kind of how this technique actually works. And there's 3 samples here, kind of overlapping. So another nice thing about this is that I mentioned that the rheometer costs about $25. The rheometer being the crystal, and then we just access that whenever we need to. So this experiment, it's a log scale in time here. So this is going from a few minutes where you kind of see solvent evaporating out to kind of a few years, kind of way out here. So you're not going to tie your rheometer up for 3 years to kind of do this sort of experiment. So this is the sort of information that you can actually get. The interesting thing here is around a day. That's when the paint is actually kind of dry to the touch. And you see this mass increase is actually oxygen incorporation into the film. And then there's all sorts of volatile compounds that come out. So if there's an alkyd, if you paint your floor with an alkyd paint, you smell it for a long time because of kind of these things that are actually coming out. And where basically this is where we kind of see a fairly kind of big uptick in the modules of the film. So it's just basically a cure monitor for a film, which is curing as it's in contact with the environment.
How do you know it's uniform? Which part tells you the film is uniform?
What's that?
Which data shows that the film is uniform in properties? There's no like separate skin layer or something else?
No, yeah. It just makes sense that it must be uniform. We don't have any data so to prove it, but if you look, it's only, let's see, well, this is normalized mass. The actual mass is about 3 microns thick. And if you look at oxygen diffusion in a glassy polymer, it's pretty quick, over 3 microns, within minutes, we're sort of equilibrated. Over here, over this long period of time, yeah, that's right. Over 3 years, it loses maybe 10% of the mass, because you have cyclic compounds that are kind of being evolved, and we have no way of telling what they actually are, but we do know what the mass loss actually is. And this is a logarithmic change in both mass and modulus over time. It shows no sign of kind of slowing down over about 3 years in time. So, and actually, if you look at kind of what thicknesses, when you start to see film, the skin effects, and the idea here is that it's all skin, basically. It's all the top surface. Even for glassy materials, the diffusion length is kind of it's bigger than that for the things we actually care about. I think that's a safe assumption in this example. What's that?
There will be no feature scale. If you have multi-layer, you will not know based on this.
Yeah, I mean, we spent a lot of time. You can actually, it's basically behaving as an acoustic reflectometer. So you can kind of, the equations to do this are very similar to equations to model like a reflectivity experiment. So you can have stacked up layers and assume you have different properties. And it turns out what you're measuring is really an average kind of all the way through. But you can look at how much that average is affected by non-uniformities, and there's not enough information in the experiment to unambiguously say what they are. So we can't say definitively that this thing is uniform all the way through. Yep. The mass? Yeah, well, this is, so 10 to the minus 2 days, what is that, 20 minutes or something? So this is just solvent evaporation. So there's alkyd and there's a mineral spirits, basically, relatively high molecular weight. So that's volatilizing here. This gets confusing with the logarithmic time scale. So it's dried out here. So I would say this is drying, just the original solvent evaporating. That's oxygen uptake. And this is kind of later stage curing reactions. We have a lot of other low molecular weight volatile species that come out. Yeah. And you know that from a lot of simpler measurements, but it's the coupling then with the mechanical properties that makes it a useful technique.
Just in terms of what films we can use, we need good adhesion, and we need good adhesion properties. And how about like development of internal stresses in the system?
Yeah, I mean, so the question is about adhesion and internal stresses. So I would say by adhesion here it really means wetting. So it doesn't need to really mechanically adhere well, but it just needs to wet well. The biggest problem with some of these things is, especially if it's something that takes a while to cure. So the alkyd paint was good because it's got it wets. We don't have any problems. Linseed oil, oil-based films, what Rembrandt was using to paint his stuff with, which the community cares about more, is trickier because it starts to oxidize and it de-wets. So you have to do creative things to actually get it to wet on the substrate. So if by adhesion you mean wetting, yeah, that it needs to be all be in contact. But the forces are so small that it's not really an issue. And also it's a thin film. So stresses, we've never seen any of these things cracking because the stresses just get relieved by shrinking kind of this direction. So that's another advantage of dealing with a pretty thin film. So, my take is the films are thick enough so that they're really representative of bulk properties, few microns, but thin enough so that equilibration and other mechanical effects like that we don't have to worry about. What's that?
Order of magnitude for the thickness can be like for you said like to prove the bulk property we need some thickness. So
Yeah, and this is a detailed technique. It depends on the modulus because basically you want the shear wave to kind of go to the top of the film, bounce, come back. So it depends on the decay length and everything like this. For a glassy film, 5 microns-ish, that regime, and you don't have a ton of leeway in what that is. Okay, this is a totally different project. So this is now kind of looking at polyatralite complexes, which I think one of the talks I think that maybe it stopped before we actually got to the polyatralite complexes. So I can show you kind of this slide from this pretty well-known paper from a few years ago from Joe Schlenoff's group. So a polyatralite complex, you just take a cationic polymer, anionic polymer with salt and mix them together. I have enough salt, I actually get a one-phase solution. So that's what's showing here. So this is the molarity of the salt. And if I take the salt away, basically I get this aggregating with this, driven by entropic reasons. Basically, the counterions get released. That increases the entropy of the system, decreasing the free energy. So there's a phase separation that you get kind of based on kind of what the salt actually is here. So we took basically the same system with lots of salt and basically kind of spun out thin films. And then we wanted to look basically at kind of what the properties kind of were of these films. So as a function of the ionic strength. So the base theories of polyatralite complexation, it's all about the entropy of the counterion. But the identity of the counterion matters a little bit too. So if it's more hydrophilic or hydrophobic, does it prefer to be surrounded by water? Does it prefer to be surrounded by the polymer? If you look at just the swelling, so you get this from the thickness measurement. So this is for a thin film, which is in equilibrium with these solutions. And you change kind of the ionic strength of the solution. And for that mechanism that I showed before, the film actually swells. So you can think of the ions kind of breaking up the ion interactions with the film, and it swells and eventually dissolves.
Which you have salt on top of and you put a sediment below, it's like a two-layer now.
Yeah, yeah,
So you're somehow reading off the amount, fraction of the two layers. So
yeah, yeah. So you these are actually this is the ionic strength in the solution that it's in equilibrium with. So we don't actually know what the concentration is in the film itself, at least from these measurements, the QCM measurements.
a bit of swelling from your shift of the phase, how do you know how much of it is swollen quartz-wet versus solvent?
Um,
You don't know what fraction.
well, no, so that's a pretty easy problem to solve. So there it's a two-layer model. So basically you're measuring, you can do the solvent itself, on top of the thing, and you're pretty sensitive to the separation. So
It's inertia part.
Uh,
Dissipation part. Which part of your measurement you're using?
yeah, I mean, it's not a direct kind of additive measure. You basically have to have a two-layer model and kind of fit to that, to what's really going on. But it works pretty well. This is a more difficult experiment than just swelling in air, for example, because you do have the liquid on top of it. But you can account for that, and you get the mechanical property information in addition to the swelling information, which is just how much water is in it. And the bottom line is the mechanical properties really are only determined by how much water is in it. So the swelling here, this is mostly due to water. So the ions could just bring kind of water into the sample, and it's the water then that actually changes the mechanical properties. So this is kind of the magnitude of the modulus versus kind of how much swelling you have. And
Because the average of the two layers or just of the bottom one?
what's that?
Phase angle you're measuring where?
That's the phase angle for the polymer layer.
The bottom one.
Yeah, that's right. I mean, the phase angle for the top one's 90. Yes, right. So all this is at base 15 megahertz. Yeah.
So it's about 45 degrees at blocks or so. Highly swollen.
Yeah, and we don't get up kind of that far. So these things are feral. There's another plot that's kind of the most useful one. This, I think, is the most useful one, kind of from this experiment. So basically, if you look at, as a function of the the salt concentration, equilibrium of these things, kind of what properties do you have? And both the phase angle, kind of on that side. So if I go to this, so blue here, up there, so that's really a high concentration of salt. Basically, I have a pretty relatively dilute solution. So at these frequencies, the modulus of water is 10 to the fifth and phase angle of 90. So water by itself would be up here. So it's not too different than just straight water. And then as we kind of drive out the water, you end up with something which is pretty glassy and a relatively low phase angle of maybe 10 degrees. So it's just looking at the kind of thermodynamics of swelling kind of these things.
If we have two layers, is always the bottom one that contributes or the more viscoelastic one? Because if you have cross-separated slicer, would you not know which one you'll be reading down there?
Yeah, I mean, there's an enormous mechanical contrast between the two. The coacervate phase is basically, or the dilute phase is basically water. And so really all we're kind of measuring, and here there's only one phase, right? And these, yeah, that's right. Down here it's two phase.
And it doesn't matter whether it's up or down, you'll still see the same thing.
We couldn't do it the other way, because if we did it the other way, the decay length of the shear wave in water is 150 nanometers. So, which, yeah, so you got to put the thing you care about in contact with the solution. That's another reason why the details of the exact what's going on the top don't really matter so much. Okay, so there's two more of these things. I might finish a little bit early here with this. So this is polycarbonate. Yep. Say it again.
There is a difference when you change the type of charge. So how do you explain that?
The difference between, oops. I mean these differences here, or? Yep. Oh, okay. Yeah. So here there's a difference, right? If you look at the modulus here, and the swelling here, there is a difference depending on these things. So the idea is that it's basically a simple way of thinking about this is basically hydrophobicity of the salt. Does the salt, would it rather be surrounded by water, or would it rather be kind of in the complex itself? And if it would prefer to be in the complex, it basically draws water with it. And so that's what's really happening with the KBR kind of one. That's known to actually be a good salt for actually kind of breaking up these interactions. So it brings in kind of more water, and the modulus actually goes down. So these ion-specific effects just tell us how much do the counterions like to be in this complex, and then how much water does it bring with it when it does that. And then the fact that these are all the same means that it's really the swelling which determines the properties. So in a sense, the ion determines the swelling, but the swelling then, which is mostly the water, kind of determines kind of what the mechanical properties are. Here.
Yeah, I just have a question about, so you say that when the counter ion likes to complex with something in the thing that's swelling,
Yep.
why does it bring water with it? Because I thought it's exchanging condensation from water to the whatever electron donating groups are in your material that's swelling.
Yeah. I mean, it is.
The water behind.
That's right. But you never. I mean, I talk about sort of the hydrophobicity of the ions, which I think is a sensible way to think about it. But they always want to have some hydration shell. It's basically, and you can calculate. It's like 8 water molecules per bromine or something like this. You can. There's some calculations based on the swelling you can actually do to figure out what that is. But that whole, basically the water with its hydration shell, depending on what the ion would prefer to actually be kind of in kind of the complex or just kind of in water. There's some things which to me are still a bit mysterious about kind of the thermodynamics and how this actually works.
Is the counter ion that's moving both the metal ion and the halide, or one or the other? Do we care about the halide, or do we care about the metal ion?
I mean, typically it's the halide that matters more. We've done some other things with this. Guanidinium, for example, it's very good at kind of breaking up, protein structures and things like this. It's a good denaturant. So if you use like guanidinium bromide, it's even kind of more effective. So they both matter, but I think it is the anion. I think largely because they're typically larger, which depends a little bit more. But I get sort of outside of my expertise on the details of this relatively quickly.
You can see by the data.
Yeah. Okay, so this is a different one. This is a more traditional rheometry experiment. So this is polycarbonate, plexiglass. This is a thin film, which it was spun cast with a bunch of plasticizer in it. And so you start here, and you kind of heat up to this temperature, and it actually drives out some of the plasticizer. Then you cool down, and this is where we actually get a series of temperature-dependent measurements. We heat up again in steps, and each of those kind of blue steps, we look at the kind of the mass that we measure, and we're decreasing kind of the overall amount of plasticizer in the sample. So this is just a way of getting kind of different kind of plasticizer amounts kind of from one sample. So from the mass, that gives us the composition. And then if we look at the There's weird stuff going on with the computer over here. Is Frederic around? Maybe you can bail me out. It's speaking to me in languages which I don't understand. Yeah.
It's just because there is no more.
Do I see?
Not completely. He's just upset about the fact that there is no more Eduroam.
Yeah, because they just cut internet, but it doesn't matter for your presentation.
It was you downloaded it, right? Because we weren't playing it from the internet, right? You had downloaded it.
Yeah.
Yeah.
So, but I think that now it works.
It does work. Okay. All right, thank you. Sorry about that little interlude. So this is basically what the plasticizer does to the material. So from those mass measurements, you kind of know the plasticizer content. So the blue one is no plasticizer. And this is the glassy regime down here. So this is anti-plasticization is kind of the name for this. So actually the modulus goes up. So polycarbonate actually has a pretty low modulus to begin with, which is presumably why it's so tough relative to other glassy polymers. And the way of thinking about this, which I think is mostly accurate, is that the modulus goes up in the glassy phase because you're basically filling up small voids. You can think about it kind of in this way. But it's a pretty clear increase in the modulus. But the glass transition itself is still going down. So you can actually see that better from here. So this is kind of the signature of the glass transition. Should be around 150 degrees for polycarbonate. And as we add more plasticizer, we're kind of driving it down this way. And there's this fairly large sub-TG relaxation peak here, which is presumably relevant for mechanical properties and toughness of something like polycarbonate. So it's very easy to see this in these high-frequency measurements. So that was the only point there. And this is kind of the final one. So this I put in because I saw out there somebody doing something with cellulose nanocrystals. So this is a deposition of a cellulose nanocrystal thin film and looking at kind of the deposition kinetics over time. So you have a dispersion of the cellulose nanocrystals kind of in water. And then the postdoc kind of developed a way of slowly kind of condensing this film, drying it out with ethanol while also keeping it flat. And you look over the drying time as kind of what sort of structures we have. And these form kind of twisted pneumatic structures which have very high modulus and high toughness if you can actually get them in bulk form. So this is the kind of the modulus on this side. So again, 10 to the fifth, that's basically water at these frequencies. And then there's kind of a rapid kind of increase. So there's a regime in the experiment here where we actually can't measure anything. That's a detail of the technique. But you see, and this makes sense, it's dilute, 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 and eventually it kind of consolidates, and then you see the rapid increase. And a shear modulus in the end for at least the thicker films of a few gigapascal, which is typical of what other people have measured with these. So okay, I only have one more slide. Well, I'm not going to worry about my one slide because it only has 2 points on it, which is the conclusion. So this was, I recognize this is a little different. I was talking a lot about a detailed technique, again, towards the end. My main kind of concluding point was really that if you have a, something where you know the elastic solution, and it's an oscillatory kind of loading that you care about, you just replace your real kind of modulus with this complex modulus, and you get the same thing. And a lot of useful things kind of fall out from that, the resonator decay time, all this sort of thing. And then I had a specific example of a kind of resonator, really, and kind of measuring things related to viscoelasticity. And you always have to remember in those experiments that we are at a very high frequency in doing this. So, yeah, that's it. Thanks very much for your attention.
Have you time for questions? Any questions? Oh, I'll start here. Why is your modulus so much strongly thickness dependent?
So the model that we have, and that's kind of the point of the paper, is that there's a soft layer up top. So the top layer is kind of a loose layer of these cellulose nanocrystals. So this is one example where I don't think it's safe to say that the properties are uniform all the way through.
And
so
so
it gets
this is the modulus at the bottom layer?
This is the average modulus of the whole thing.
So you always measure the average. You don't measure the bottom one, because that was my question earlier.
Yeah, that's right. I mean, in this case, what we did is a two-layer model and say, okay, we always have a modulus close to this at the bottom. And then there's a layer at the top, kind of one layer basically of the cellulose nanocrystal.
But it looks like it's a factor of 10 down, so it looks like it's 10 to 1 volume ratio.
Yeah, that's right.
So it's mostly top dilute something and a very very thin, stiff thing.
Yeah.
And the phasing, what is this? The phase angle? What is the other plot? The phase angle is also very different.
Yeah, I'm not so worried about this. In terms of, it's a little bit trickier to get that in these experiments. But here we can't say definitively, but I think the most sensible way to do is take a simple two-layer model, and we show that these are the numbers you get if you have it's just really a surface effect.
So you can do just fracture through and just measure with microscopy.
We did that if you do, this is a contact mechanics example I was also thinking about showing. So you can use basically AFM indentation and measure the modulus on kind of both sides. It doesn't quite work out that way, because as soon as you do the indentation, you're looking at the free surface again. So there's no way to really get at the properties of a confined surface, in contact with our substrate. But I think the sensible explanation here is that there is a layer at the top, which is just softer.
What's the difference of modulus or difference of density?
The density? Well, all these things have densities not too far from 1. So, yeah, that's right. The cellulose nanocrystals are, I don't know, maybe they're 1.2 or 3 or something like that, but it's not different enough to explain much of that. So it's definitely in the modulus.
But you're measuring inertia, effectively, inertia of the layer, this technique.
Well,
in phase.
Yeah, there's an inertial limit of the thing when it's really thin.
But you're measuring the inertia by the technique, how much mass, the mass of the layer.
That's right.
Okay.
Yeah.
Other questions? Go ahead.
Sir, in your last example, so you said you reached a cholesteric phase basically?
Sorry, I didn't hear that one.
Sorry.
It's not you, it's my hearing is not so great. But
You said that you reached a cholesteric phase, is that correct?
yes, yeah.
So I assume that you go from isotropic to maybe pneumatic and then parallel pneumatic? Yes?
I believe so. Yeah.
So can you follow the phase transition?
With other means, but not necessarily by this one. I don't think there's quite enough information here to know exactly where we're at. Yeah. Yeah. And I don't know when you're. This is not the best way for that particular experiment.
Okay, let's thank Ken once more.